In this lecture, we look at Pascal's principle. This principle states that a change in the external pressure to an enclosed incompressible fluid makes the same change to the pressure in all parts of the fluid and to the walls of the container that the fluid is in. Here we have our container. It has a piston on top, and we're going to be pushing down that piston with some force, or changing the pressure on top of this piston. So the pressure at some depth d in the fluid is equal to the external pressure that's being applied plus rho, the density of the fluid, times the depth times g. Well, if we change that pressure, or change the force, we see that the only thing that changes is the first term. The second term, the part that's circled in red, doesn't change as a change to the external pressure. So that the change in the pressure throughout is equal to the change in external pressure. Now let's rearrange our apparatus down at the bottom with another little piston on it. We're going to apply a force F in on that piston, and then I'll create a force F out attached to the top piston, coming from the top piston. Well, the change in pressure is at the bottom piston is equal to the force in divided by the area of that little piston. But the change in pressure is the same as throughout, so this is also equal to the force out divided by the area of the out of the bigger piston on top. We can then rearrange this so we find that F out is equal to A out divided by A in times the force in. So that since A out is much bigger than A in, the force out is much bigger than the force in. If the input piston moves a small distance delta x in, how far does the output piston move? Well, this is an incompressible fluid, so V out must be equal to V in. A out is delta x out, which is equal to A in times delta x in. Rearranging this, we have that delta x out, the amount the out piston is moving, is equal to A in divided by A out times delta x in. So if the area of the output piston is much greater than the area of the input piston, as it looks like in the picture, we have that delta x out is very much smaller than delta x in. We can look at these two ideas in terms of the work. The work that's being done by this machine should be equal, so the work in is equal to the work out. Well, the work out is the force out times this delta x out, which is equal to A out divided by A in times the force in, that's the force out. And delta x out is equal to A in divided by A out times delta x in. These two cancel, and we see that we do find that W out is equal to W in. Let's look at the example of lifting an elephant. An elephant with a mass of 1,500 kilograms stands atop an output piston, there, and a sheep with a mass of 50 kilograms is atop the input piston, there. So the question is, which goes up if the area of the output piston is 20 meters squared and the area of the input piston is a half meter squared? For the elephant to rise, F out must be greater than the weight of the elephant, or the mass of the elephant times g. So there are the forces. F in is equal to the mass of the sheep times g. So if we use our formula that F out is equal to the area out divided by area in times F in, we have that 20 meters squared divided by a half meter squared times 50 kilograms times g is equal to 20,000 newtons. Well, the weight of the elephant is around 15,000 newtons, so the elephant rises.